Hello everyone. This is the second lecture of the course Statistical Thermodynamics. The topic of this lecture is a brief look at the history of statistical thermodynamics. Statistical thermodynamics or statistical mechanics was developed around the end of the 19th century, that is, approximately 150 years ago. It was developed a few years after classical thermodynamics and a few decades before quantum mechanics. I would like to give you a broad sketch of the events that led to the development of statistical thermodynamics. If you are asking why is this useful, my answer is that everything that you do does not have to be useful. Life is about doing interesting and fun things and not just useful things. Anyways, in the context of our present topic, I think it is just interesting to know when and where the knowledge that we are engaging with was created. What were the events that led to this knowledge being developed? Why did it develop in a certain part of the world and not somewhere else? What sorts of leaps of imagination were involved in developing this new way of looking at the world? One of the major factors driving the development of the science of thermodynamics was the development of heat engines, which happened in Europe starting around 1700. A heat engine, as you know, converts heat energy to mechanical work, and the heat engines being developed in Europe in the 18th century were essentially steam engines. Note that heat engines were designed and used commercially before the science of how they work were known. So, this is an example of a technology coming first and the science later. History has shown that both sequences have happened abundantly. Science leading to technology and technology leading to science. Another interesting point to realize while talking of heat engines is that although humans have used mechanical energy for centuries, for example, to plow fields, to grind grain into flour, extract oil from seeds, pump water, and travel long distances, the source of this energy before 1700 was primarily wind, flowing water, and animal muscle power. The concept of using fossil fuels to generate mechanical energy was not there for most part of human civilization. The first commercially successful steam engine, technically a steam powered pump which did not have any moving parts, was built by Thomas Savery in 1698 in England. The concept of heat at that time was not what it is today. Heat was not thought as a form of energy. This might sound surprising to you, but take a moment to think why this was the case. Heat as we experience it has no obvious connection with motion, and motion is what is associated with energy. So, for today's high school students who parrot that heat is energy, the only reason for doing that is that they have been told the statement by their teachers and books and have accepted it after being told many times. The idea of heat in the 18th century was that of an invisible fluid called caloric, which flows from a hot body to a cold body. This was suggested by Antoine Lavoisier, the same person who revolutionized chemistry by proposing the modern theory of combustion. Coming back to heat engines, the engines of those days burned a lot of coal to produce a relatively small amount of work. There was a lot of interest, therefore, in improving the efficiency of engines. One of the most influential works in this context was by French mechanical engineer Sadi Carnot. He published a book in 1824 in which he presented the first successful theory of the maximum efficiency of heat engines. He is often described as the father of thermodynamics. About 2 decades later, in 1843, James Joule experimentally showed that mechanical work and heat are related. In fact, using very precise measurements, he found that whenever mechanical force is expended, an exact equivalent of heat is obtained. This suggested a connection between heat and motion, an idea which today we take for granted. But at that time, this was a major conceptual leap given that heat was associated with the caloric fluid. His work also suggested that heat could do mechanical work and that energy is conserved. In 1850, German physicist Rudolf Clausius published a paper on the theory of heat, rejecting the caloric theory of heat and proposing the first formulation of what would be known as the second law of thermodynamics. He also explicitly stated the first law of thermodynamics. In 1865, he published another important paper in which he introduced a new thermodynamic state function which he called entropy and expressed the second law of thermodynamics in terms of entropy. In 1859, Scottish physicist James Clerk Maxwell derived from the mechanics of individual molecular collisions the expected distribution of molecular speeds in a gas. This was the first statistical law of physics. Austrian physicist Ludwig Boltzmann built on this idea of the statistical distribution of properties of molecules, and in 1877 he published the famous equation S is equal to K ln W, which expresses the relation between entropy and probability. He is the one who really laid the foundations of statistical thermodynamics. American physicist Josiah Gibbs provided a more general formulation of statistical mechanics than Boltzmann and introduced the idea of the microcanonical, canonical, and grand canonical ensembles. He coined the term statistical mechanics, which was in the title of the book he published in 1902. Interestingly, the subtitle of his book is The Rational Foundation of Thermodynamics. I think you will understand the appropriateness of this as we go along in the course. Most of the ideas we will discuss in the course was developed by this point in time. As we explore different concepts during the course, the work of the scientists we have talked about will come alive, and you will get a much better appreciation of the fantastic imaginative genius of these people. From the next lecture, we will begin discussing the core subject matter of the course. As you know from the course contents, we will begin with a review of classical thermodynamics and continue with that thread for the next few weeks. See you for the next lecture.